So let's start with the history behind SCTetra. Especially in mid-90s to late 90s, the need for CFD or even CAE in general increased so much because a lot of large companies such as automotive OEMs, their suppliers, machinery companies, they wanted to develop their products quicker, better, and with a less cost. So because of that, a lot of companies started to look into the utilization of CAE. And probably many of you remember how shocking it was when the Windows OS came out. And also PC spec quickly evolved in late 90s. When we saw these situations in the market, we wanted to pursue the development of practical CFD software, which can be used on Windows. Because traditionally, most of the CFD software were on Linux and Unix, very difficult to use. We wanted to provide the CFD software that is so practical that ordinary engineers can use it to enhance their product. So that was our motivation. And to do that, the software has to be easy enough so that the ordinary engineer can use it. It has to be fast enough so that they can apply in their daily work, and has to be accurate enough so that they can really rely on the results. Finally, we came up with the first version of SCTetra in 1997, and that was on Windows. It was all-in-one package, which is part of the ease of use. Because, again, traditionally, CFD software companies used to produce only the solver. But in the end, the user has to do pre-processing and post-processing as well. So we wanted to provide all-in-one package CFD software. And I believe we are the first commercial CFD company to provide all-in-one package, and especially on Windows. And because of that success, we have been awarded by several organizations in the past. Especially in 2005, we were awarded by Ministry of Economy, Trade and Industry of Japan. And we are very proud of this award because the government of Japan itself acknowledged our contribution to the manufacturing society. So this all-in-one package CFD software that comes with preprocessor. Let me show my laser. So preprocessor, solver. Now, our SCTetra solver has 4 solvers inside. Pressure-based finite volume method solver, which is usually for low-speed applications. Density-based finite volume method solver, which is usually for high-speed, especially high Mach number applications. A joint solver for shape optimization. Linear static structural finite element method solver. And then we have post-processor optimization tool. And we have many capabilities to couple with various software. And these are just some examples of applications that our customers have been using. A lot of OEMs in automotive, suppliers, machineries, fans, pumps, turbines, biomedicals, aerospace, marines, all kinds of industries. Now, finally, I want to start talking about ease of use, fast and accurate part of SCTetra. Let's start with pre-processing side. So this is the GUI when you open the software. And once you import the geometry, you see a tree on your left-hand side. We call it navigation tree. The idea of this navigation tree is to really navigate you from importing the geometries to recognize closed volumes, to specify material properties, to specify regions, and to specify analysis conditions. Well, after that, of course, we have to create the mesh and we have to execute. Now, when it comes to specifying specific conditions, that could be quite complex. That's why we have another condition wizard. the first page of this condition wizard allows you to choose what kind of physics or what kind of special functions you want to use. And according to your selections about the physics and functions, again, this tree gets longer and longer. The idea of this condition wizard is to guide you to only necessary pages so that people who may not have much CFD experience can easily, efficiently, without any omission, can specify what needs to be specified. So in general, our GUI is trying to navigate you to only necessary pages and items. Now, you might ask me, so what kind of data can you really import? We try to support as many file formats as possible. Starting from native CAD data, we can import CATIA V4, V5, ProE or Creo, Inventor, SolidWorks, NX, Solid Edge. Now, you might say that, oh, I only get intermediate files from other engineers or designers. So for those situations, SCTetra is capable of importing PowerSolid, STEP, STL, DXF, IGES, AC file, or VDA, FS file. Or you might say that you might be already doing some kind of CA simulations and you do have existing meshes. In that case, SCTetra can import Nastran format, universal file format, Abacus input file, or TGNS, or TechPool formats. And all of these files can be just simply dragged and dropped onto our software. So it's kind of a Windows-like operation. People who might be doing CFD or CAE, you might say, well, okay, I understand about data import, but what about cleaning? So I'm glad you asked. Our concept is to really provide all the tools that engineer needs to perform CFD simulations. That's why we also developed a lot of capabilities regarding data cleaning. So this page, I'm not going to explain in details, but I just want you to know that, first of all, we have a solid level cleaning and modifications capability. And there are many capabilities. Some of them are automatic. If you choose to do manual way of cleaning, you can do that. Now, most of the cleaning itself can be done automatically, but when it comes to modifications, for example, this cat model, there are several kind of ribs that might not be necessary for CFD simulations. So you want to modify it. When it comes to modifications, you have to put your intention to modify. So most likely those are manual operations. But we have so many ways to modify the geometries. And when it comes to surface level cleaning and modifications, again, we have so many different capabilities. Most of the cleaning part can be done automatically. And if the automatic cleaning on the surface level did not work well, we still have many manual operations that allows you or empower you to clean the geometries. Part of data cleaning or preparation, I would like to talk about wrapping. So this is a car geometry, especially you are looking at the underfloor of the car. As you can see that the geometry is pretty complex. And I want you to focus on small features within the red circles. You see very small circles or small fillets or small gaps. If these small features are not necessary, you want to clean them, but cleaning one by one might be very cumbersome. Now, this wrapping is like you take a piece of cloth and you wrap an object so that you have a smooth surface outside. That's exactly what this wrapping does. With next click, you will see that geometry is cleaned, so please pay attention to small features within red circles. So I hope you saw that all those small features are gone. Now, the beauty of this wrapping capability is that it's 100% guaranteed to give you watertight geometry or ready-to-be-used geometry. I like to move on to mesh resolution control using Octree. This ties to ease of use, fastness, and also accuracy of the simulation. Using Octree system is somewhat unique to SCTetra. Octree is shown in pink cuboids. So all these pink cuboids that you are seeing, these are called octants. The top image is showing that rubber box in black. This rubber box is used to specify this region to refine. So you choose this region by rubber box, and it's refined. Now, all these cuboids are just part of control. It's not the mesh yet. And depending on those specifications, the preprocessor will mesh it. So this is the result mesh. Now, in addition to specifying the sizes to the surfaces and regions, you can utilize these octants. The main reason why we have this is that you can visually control the mesh sizes in any arbitrary points and regions in space, and I want to emphasize in space. Just to remind you, we are not simulating the behavior that is happening in the solid or among the solid surfaces. Like, FEM, you care about the solids. But we do care about something that is happening outside of the solids, which is the fluid region. The controlling the mesh only along the solid surface is not good enough for CFD. That is why we came to utilize this octant system, which allows you to refine the mesh where only it is necessary. That is why SCTetra can enable you to accurately and efficiently simulate your program within the limited resources. So accuracy and efficiency. Now, speaking of mesh, if you don't know where you should refine, then that might be a problem. For that kind of situation, we have a capability called adaptive mesh refinement. What you see here is an example of a cylinder port in the engine. As a user input, you specify the number of elements that you want to use as the maximum, and you specify the number of iterations of the solvers. What's going to happen is that, depending on these specifications, the preprocessor and solver will automatically create the first mesh. It's a rough mesh, and using that rough mesh, you came up with first result. And using this first result, program automatically refine the mesh by detecting the gradients of the pressure and velocity and temperatures, and then get the second result. And using the second result, repeat this process. Remesh it, get the result, remesh it again, and get the final result. Now, by comparing the third and fourth results, you can tell that the results are almost the same. So by comparing these, you can see that, for this simulation, you need this kind of mesh resolution and these kind of number of elements. So this helps you if you are simulating something for the first time, or if you don't know where to refine. Even for expert CFD users, when you are dealing with complex geometries, sometimes you are not aware of exactly where abrupt physics is happening. So this capability helps you a lot. Part of easiness and fast about the software, our preprocessor can create mesh pretty fast. To give you an example, SCTetra can create 50 million elements containing several prism layers on a complicated formula car. So I want to show you what the prism is. So this is a prism shape. Now, these prism layers are used for so-called boundary layers. Having these prism layers in the boundary layers are very important for the accuracy. And a lot of automotive companies told us that our measure is probably a couple of times faster than other software because we can create in just 15 minutes, including prism layers for 50 million elements. Now, I'm just talking about using the standard license. We also have a parallel license for preprocessor. With that, you can even shorten the meshing time. Now, to let you know that usually in CFD, you probably use 10 to 100 times larger number of elements than FEM. So here I mentioned about 50 million elements, but nowadays a lot of OEMs and racing companies, they use 100 million to maybe 300 million elements to simulate external flow simulation of the car. So being able to create mesh fast is very important. Now, I want to start talking about accuracy part. Accuracy is often a trade-off with the speed and memory consumption. In general, the more elements you can have, basically you can aim for better accuracy. Now, with SCTetra, you can handle about 3 million elements with 1 gigabyte of RAM. So if you have 64 gigabytes of RAM available for SCTetra, you can handle up to 192 million elements. And I want you to look at this chart. SCTetra is shown in blue bar. There are a couple of high-end CFD software, and there are a couple of entry-level CFD software. Now, on the vertical axis, it shows the number of elements that each software can handle using 1 gigabyte of RAM. This chart might be a little bit too small for you. Hopefully you can see it. SCTetra can handle 3 million elements using 1 gigabyte of RAM. And most of the high-end CFD software can handle about 1 million elements. And entry-level CFD software can handle about 0.5 million elements. So that tells you how efficient our solver is. And this is one of the reasons why we can handle more complex geometries, or by having more elements, you can aim for better accuracy. This is one example of ball valve simulation. A company called Kitamura Valve in Japan, when they started to investigate about CFD, they didn't have much CFD experiences. So we provided a benchmark test and provided that data, and engineers were pretty surprised in a good way that we can predict with a good accuracy. So he took those data that we simulated, and he also imitated for different ball valve angles. And he was able to predict with good accuracy. Now, this is a performance curve showing that as the ball valves open, the horizontal axis shows the degree of openness, starting from 10 degrees to 90 degrees. And then the vertical axis shows the flow coefficient. You can think in terms of flow rate. So as the ball valve opens, there's more flow that is flowing. Now, blue line indicates the CFD results, while red line indicates experimental results. So as you can see, the agreement is pretty good. This is another example of aerodynamics of a car. This is pretty unique because this is organized by Society of Automotive Engineers in Japan. They came up with the conceptual car. They made a clay model, and they also performed internal tests, and they asked the vendors to do a blind benchmark test. So as a Cradle, we participated in this event. So the top table, experimental results shows that coefficient of drag was 0.245, coefficient of lift negative 0.273. SCTetra predicted as shown here, and the difference or error was less than 1%. So we are very happy with this result. Now, Cradle started in Japan, and we have been working with Japanese and Korean automotive companies very closely. So that's why we have a lot of know-how how to simulate parts, components, and entire car with a good accuracy. Now, the table below, or the chart below, also shows the comparisons among different CFD software, starting with the experimental result on the top. So this black bar, starting from 0, it extends to 0.245. This red dotted line indicates the experimental result. One of our competitors predicted, but under-predicted. Another software did a little bit better, but actually SCTetra performed even better, or actually the best. Similarly, for coefficient of lift, starting from 0, equals to negative 0.273. So again, this is the experimental results line. One competitor under-predicted. Another competitor did pretty good, but SCTetra predicted even better. So hopefully you start feeling that SCTetra can predict with a good accuracy. This is another example of a pump manufacturer called Tetra. It's one of the centrifugal pumps. These charts are called something called PQ curve, characterizing the relationship between static pressure and the quantity of the fluid you can push. Now, for fans, usually called PQ. I should have said this is the HQ curve, because most likely pump manufacturers use hydraulic pressure, and so that's H. But the point is, the blue line indicates the simulation results, while orange line indicates the experimental results. Again, as you can see, the agreements between the experiment and the simulations are pretty good. So this company started to utilize SCTetra a lot for their development of the pumps, and they developed so many different kind of pumps. They also gave us testimonial comments, and I want you to look at the bottom sentence. Basically, they were saying that they were able to reduce the development time by 25 to 65%. And of course, that directly relates to the cost as well. So I want you to understand, we are not talking about the computation time. We are talking about the development time itself was reduced by 25 to 65%. And that's exactly what we want to contribute to all the customers by providing a practical tool. And another example of the ship hull. The drag of the ship hull is pretty crucial. So a lot of ship manufacturers, they try to predict and optimize the design of the ship hull. Experimental results shows somewhere between 52.8 to 54.48 newtons, and using SCTetra, we predicted 53.14, so it's right in the middle. Another example of a ship propeller. Now, when the propeller rotates really fast, it creates cavitation or cavity, which is basically small bubbles. And I want you to look at this animation, well, actually the video with the animation. On your left-hand side, it's coming from water tunnel test. And you see those cavitation here. And SCTetra was able to capture those cavitations pretty nicely right here. Traditionally, pump manufacturers and ship propeller manufacturers did not think that CFD is ready to capture this kind of phenomena. But with SCTetra, which consumes less memory and has capability to refine as you like. And because of those capabilities, we were able to predict with good accuracy, even considering these cavitation. And now I want you to look at the top numbers here. There is something called thrust coefficient, which is to characterize the performance of the propeller. Experimental results show 0.3725, and our results was 0.375, which was deviated by the experiment by only 0.67%. And again, hopefully you start feeling that SCTetra can predict with a good accuracy, even including this kind of complex physics. Now, you may ask why SCTetra can do the simulation accurately and efficiently. Actually, I should also mention that most of the customers told us that our software, our solver is pretty fast, and sometimes people say 2 to 3 times faster than other software. Now, the difficult situation is that it is very difficult to do apple-to-apple comparisons, but a lot of customers did tell us that they feel, they can feel easily that SCTetra is so much faster. Now, one of the schemes that we are using in SCTetra is so-called vertex-centered control volumes. After you create hybrid mesh consisting of tetra mesh, prism, pyramids, hexameshes, the solver internally creates polyhedron control volume by using vertex-centered schemes. So to give you an example, so these black line indicates the elements, and let's say tetra elements. And using medians of all those lines, the solver creates polyhedral elements like that. And that's the control volume. So in 3D, it's like this, polyhedral mesh, basically polygons. Because the polyhedral mesh has more number of polygons, which means we deal with so many fluxes from different directions. For the programming sake, it's more difficult, but in terms of the accuracy-wise, it becomes more accurate. And because we are using less number of control volumes, if you use the number of elements, that's significant, but then we convert them into a polyhedral control volume, which is less number of control volumes. That's why we can solve efficiently as well. In terms of physics and functions, we have a lot of functions. We can handle like compressible flow, incompressible flow, Newtonian and non-Newtonian fluid. We have heat radiation, solar radiation. We have LES, DES, GLES, 12 different turbulence models for those who are interested in turbulence modeling. Multi-phase, free surface, particle tracking, humidity, condensation, solidification. So you can see that we have all kinds of physics here. Because in the end, engineers are dealing with real physics. So we want to provide those physics as well. So I want you to know that SCTetra is very rich in functions. Relating to mesh technologies, we can handle all kinds of motions. I'm going to show you in the following slides. One function related to meshing is called overset mesh. This is pretty unique to SCTetra. This is an example of intake valve in the cylinder of the engine. Now, you are seeing two meshes here, red mesh and blue mesh. Those meshes are independent, especially the valve is moving up and down within that red mesh. So this mesh, red mesh, is the moving mesh on top of the blue mesh, and the values are interpolated between blue mesh and red mesh. since two meshes are overlaid, that's why this method is called overset or overset mesh. This overset mesh allows you to handle motions like this, which is to close and open. Sometimes people call it pinching motion of the fluid, because when you consider about the mesh, traditionally you have to shrink and stretch to handle this kind of motions. But using overset, you can fully close and you can open from the closing positions. Now, using this overset mesh, you can start simulating so many different kinds of motions. All these pumps that you are looking at, or some of them are pumps, some of them are valves, some of them are blowers, but all of these have something to do with motions that has contact. Top left, it's a scroll compressor or scroll pump. Right hand side, it's a ball valve. Again, you see that ball valves are closing and opening. Gear pump, lobe type pump. All of these, traditionally, it was very difficult. But with the overset mesh, now you can simulate much, much easier. And this overset mesh can be combined with further, more advanced physics as well, especially with free surfaces, which is actually one of SCTetra's advantage too. Top left, you see that water flows and that rotates the water mill. So that's an induced motion. Top right, water flows out from the spindle and that rotates this device. This is actually an electricity generator. Bottom left, it's a very simple, simplified geometry of like a gearbox. But again, two gears coming together, traditionally it was very difficult. So overset allows that, and then you can combine with the free surface capabilities to see oil splashing. The right bottom, it's a ship floating on the wave. That is a 6 degrees of freedom. Wave carries this ship in all directions. Now, furthermore, this overset mesh actually helps fluid structure interaction as well. This example is a very simple example that we came up first. It's a rubber. Initially, it was bent and then released. You see that the rubber moves back and forth, which affects the flow to be generated. But anyway, as you can see, we can handle quite larger deformation, and that can be done because of the overset mesh. The left bottom animation is a classic example of fluid structure interaction validation. Air is flowing from left to right, and that generates the oscillation of the plate. So it's a classic validation case. Now, bottom right, it's an example of a road sign that is oscillating because of the strong wind. So next time when you are driving in a stormy day, I want you to look at the road sign. Probably you see that the road sign is quite shaking and oscillating. Now, the last slide for the overset mesh, I want you to show this one. This is an example of a reed valve. Now, let me play. A piston is moving from bottom to up. As piston moves up, pressure builds up, and that pushes this reed valve to open. Now, I want you to focus here. This reed valve is flexible, so it's a fluid structure interaction, and it starts from complete closed position, and then again, so piston is coming up, pressure builds up, and that pushes the reed valve to open, and it goes to the top, hits the ceiling, and comes back. So because of the overset mesh, you can simulate this kind of phenomena as well. Now, you might be interested in coupling SCTetra with other physics. Just to give you some example, with the structural analysis software, we have our internal program, SCTetra. So you can do a simple linear static structural analysis within our platform, or you can use our mapping tools to map to NASTRA files, input files, universal files, SEMPED, and adventure cluster files to do one-way structural analysis. We can couple with acoustic simulation software. MSC, by the way, has Actron. We can also couple with other acoustic software. We also have optimization tool, and we can couple with other optimization tools as well. We can couple with electromagnetic software, 1D simulation software, chemical reaction solver, and morphing tools. Since I mentioned about Actron, I just want to give you just a feel of how that coupling between Actron and SCTetra can do. First of all, when you have a geometry, you start with the CFD, SCTetra. You simulate using CFD and export into so-called CGNS file, and give this CGNS file to Actron, and Actron can regenerate the noise source, and then it can simulate the propagation of the noise. Now, Actron is so unique that it can perform in two ways. In general, noise itself is a transient phenomena. It's a fluctuation of the pressures. So technically speaking, it has to be a transient simulation of a CFD and also in acoustic. But that kind of simulation takes pretty long time. Actron has a capability to utilize steady-state simulation from CFD, and using stochastic SNGR, that stands for stochastic noise generation and radiation source. Anyway, using this capability, you can do quick simulation and investigation of acoustic. It might not be so accurate, but when you are going to perform relative comparisons among different design ideas that you have, this method could be very beneficial. I want to give you one example of an optimization that we have done. It's a bobsleigh. Now, I don't know if you're familiar with the bobsleigh sport. Bobsleigh is called Winter Formula One because this bobsleigh, basically you slide on the ice, and that can go up to about 100 miles at the top speed. And probably, as you know, that as speed increases, drag increases by velocity squared. So aerodynamic shape is a very important aspect of the design of the bobsleigh. Now, traditionally, Japanese bobsleigh teams, Japanese national bobsleigh teams, they have been using foreign countries' bobsleigh machine. And there are several, actually more than 100 small companies in Japan gathered together to develop made in Japan bobsleigh. And Credo decided to participate in this project to contribute to the aerodynamic design. Oh, by the way, this bobsleigh has a flag. It's a Jamaican flag. Jamaican team, national team, decided to utilize our design. So what we did was that we started with existing bobsleigh model. We did a 3D scanning, created a CAD model. Using SCTetra and SCTetra's automation and optimization tools, we optimize the shape. A little bit in details, there are 14 design variables. So you can see there are different sections which we parameterize to come up with so many different combinations. The objective of the optimization is to reduce the drag while increase the lift, actually downforce. So it's not really a lift, but downforce. So that was the objective. Because there are two objectives, that's why it's called multi-objective optimizations. In the end, the initial model had a coefficient of drag 0.33, a coefficient of lift 0.007. With our optimized shape, we came up with 0.278 for the coefficient of drag and negative 0.129 for coefficient of lift, which is the downforce. So as you can see that we drastically improved the performance. So we are very happy that we were part of this project. Now, the initial intention was that Japanese Olympic team would use this machine. I guess there are many other aspects that are important for them. So at this moment, Japanese team is not using, but at least Jamaican team decided to use our design. In 2008 Winter Olympic, they are going to use our bobsleigh. So when you see bobsleigh Jamaican team competing using the bobsleigh, know that it's our design. Now, I want to give some additional information. We have company brochure, product brochures. We have brochures by industry. We have a lot of customer interview articles, probably more than 40 interview articles. We also have one-page case studies focusing on functions, focusing on physics, focusing on applications. There are probably more than 50. Also, if you go to our website, there's a page listing a lot of terminologies related to CAE and then especially CFD. You might want to know something about CFD or basics of CFD, or a little bit advanced topics such as multi-phase, turbulence modeling. We have many articles about those. We also have on-demand webinars. Many of them are free. So if you're interested in these, please go online and check them out. So that concludes my presentation. Thank you very much for your attention.